All right, I think we're gonna go ahead and get started. So the plan for today is to start off with the main kind of technical meat for this course. So as I mentioned in the previous lecture, the main kind of motivating example that we're going to use as a unifying theme throughout this course is quadrotors. So just to give you a sense for what modern kind of quadrotors or drone systems can do, this is a video from Skydio, which is the largest US-based drone manufacturer. And what they're doing is basically aerial photography and aerial inspection applications. So the video is showing some of the kind of capabilities that systems today are capable of. The final project for the course, as I mentioned, is going to be due to vision-based navigation completely autonomously. And we're going to kind of slowly build up towards that ultimate goal. Here's another video just as motivation. So this is some work that I was involved with at Stanford. This was in a lab setting where the goal was to take this drone, take this quadrotor, and make it navigate through these kinds of hoops at relatively high speeds. All right, so we're not going to do that quite yet, so we will get to that kind of thing closer to the end of the course. For now, just for the first kind of module on feedback control, we're going to basically concentrate on what might be the kind of simplest behavior you could feasibly ask for from a drone, which is simply to hover. So just hover in place, do nothing in a sense, or nothing interesting maybe. But as we'll see, actually there's quite a lot of interesting stuff that goes on just to make a drone hover. So for the next 4 lectures, we're going to develop techniques from feedback control theory to make a drone hover in place. And the approach that we're going to take, you can think of as kind of like a 2-part approach. So the first part has to do with dynamics. So figuring out how the drone moves, how the drone behaves when you apply different commands to the propellers. So if you ask the propellers to move at different speeds, what impact does that have on how exactly the drone moves? So that's the study of dynamics. And then the 3 lectures after that, we're going to think about feedback control. So once we understand the dynamics of the system, once we understand exactly how the drone behaves, can we figure out some mechanism for correcting for deviations from your target goal? So if you want your drone to hover here, let's say there's a little wind that comes and blows the drone away, or maybe there's some imperfection in your model of the dynamics of the system. How can we make sure that we correct for those kinds of disturbances or some uncertainty that you have in the dynamics? So that's roughly the plan for the next 4 lectures, which are going to focus on dynamics and feedback control. So I'll just kind of mention a couple of comments here. So there are entire courses that can be devoted and are devoted to each of these topics, so to dynamics and control. So if you're in MAE, then you've probably taken MAE 206, which covers a lot of the material that we're going to kind of briefly sketch here in this course. There's also MAE 542, which is being taught this semester, so that's the advanced dynamics course, which covers Lagrangian and Hamiltonian mechanics. And we have a number of feedback control courses, MAE 433, 434, 544. So if you're in MAE, again, maybe you've taken 433, for instance, and some of the material we might cover in these next lectures might seem familiar, but then we're going to cover other things that might be less familiar to MAE students. We're only going to cover enough material of dynamics and control just to kind of understand how the feedback control system for a typical robotic system works, and to develop enough techniques to allow us to reliably control the drone to this kind of hover configuration. One benefit of starting off with dynamics and feedback control is that it allows us to establish some of the notation and terminology that we're going to use throughout this course. So I'll try to emphasize that. Again, some of the terminology might be familiar to you, depending on what major you're coming from. Some of the terminology might be unfamiliar, but either way, we're just going to make sure we're clear in terms of the terminology, and we're going to use that terminology throughout this course. Another thing I'll mention is, even though I'm using drones as motivation for a lot of the technical material that we're going to cover, many of these techniques actually apply to other robotic systems as well. So in particular, when we're thinking about feedback control, the techniques we're going to introduce can also allow things like this. So a humanoid robot balancing on one leg. So it's not quite doing it perfectly here. In fact, it falls completely. But yeah, if we think about this task, it bears some similarity to the task of making a drone hover. So you're essentially correcting for deviations from some target goal that you want your system to be at. So yeah, that's kind of the plan. We're going to start off relatively simple or simplified. We're not going to look at the full 3D quadrotor just yet. We're going to start off with a planar model of the quadrotor. So just imagine, so it's really a birotor. So you have 4 propellers, but just imagine that you're kind of looking at it from the perspective that you're looking at it from. But then the motion is constrained just to be in the plane. So that's what I've illustrated here on the slides. And we're going to say there are just 2 propellers, or maybe like 4 propellers where you aggregate 2 of the propellers. So you end up with 2 thrusters, essentially. And you can control the thrust forces of these propellers. So F1 and F2, we're going to call those our control inputs. So we can directly command these motors to produce a certain thrust, F1 and F2. So F1 is the thrust produced by this motor. F2 is the thrust produced by the right motor. Okay, I guess any questions on the motivation or setup? I'm just going to switch to the blackboard now. Maybe just a quick kind of handwriting check. So my handwriting, I'll admit, is not always super clear. So maybe just at the back. Does that seem okay? All right, mostly thumbs up. Okay, good. If at some point something is not clear, just call out. Because yeah, like I said, it's not always going to be completely clear when I write. But yeah, just ask me and I'll be happy to write slightly larger or just say what I've written. Okay. So we're actually going to start off with an even more simplified version of the planar quadrotor than I presented on the slide. So this version only moves in one direction. So imagine the planar quadrotor with its 2 propellers. But imagine that the orientation, so the angle of the quadrotor is completely fixed. So it's constrained to be in this horizontal configuration. And the only allowable motion is in the vertical direction. So in the Y direction, if you like. So let's say this is the origin of some inertial reference frame, some reference frame that's attached to the ground or to your lab. And you have 2 directions, X and Y. But there's going to be no motion in the X direction. So all the motion is going to be purely in the Y direction. And again, we have these thrust forces, F1 and F2. So this system, the way I've described it right now, has 1 degree of freedom. So we're going to abbreviate degree of freedom as DOF. And roughly, so just intuitively, degrees of freedom are the number, let's write it out. So the number of independent ways a system can move. In this case, we can just look at the system and say there's 1 degree of freedom, so we can only have motion in the Y direction. So I can use just 1 number, so the Y height, if you like, away from the origin, to completely describe the configuration of the drone, right? So again, the orientation is completely fixed. So if I just tell you what height the drone is at, that fully specifies the configuration that the drone is in. We're going to look at systems with higher degrees of freedom in just a little bit, but hopefully it makes sense that because there's only one independent way this thing can move, this has 1 degree of freedom. Okay, so the next step will be to try to understand the dynamics of this 1 degree of freedom system. So how does the system behave? How does it move when we apply different thrust forces from the propellers? So we're going to use Newton's second law here. To derive equations of motion, equations that describe how this system moves. So yeah, Newton's second law, mass times the acceleration. So let's say the mass of the drone is little m. Y double dot, that's the acceleration of the drone. Again, everything is just in the y direction. So y double dot is the acceleration. Equals the total forces that are acting on the system. So there are 3 forces total. So there's the F1 and F2, the thrust forces from the propellers, and also the force of gravity. So let's say we have gravity pointing downwards. So we can write m times y double dot equals F1 plus F2 minus the force of gravity. Okay. We're just going to define a quantity that we'll call U1. And just a kind of note on notation. So an equal to sign with a triangle, that's what I'll use for a definition. So I'm defining a quantity U1 to be F1 plus F2. So this is basically the total thrust from the propellers of the drone. So we can rewrite this equation that we have. So we can put y double dot on the left hand side, F1 plus F2. We're going to call this U1 just to make the equation slightly more compact, and because we'll use this notation later as well. So U1 minus mg. Or I can write it as U1 divided by m minus g. Okay, and I'll label this as equation 1. So this is a differential equation, and this basically tells us how the system is going to behave. So if I prescribe a particular value for U1, so if I prescribe a particular total thrust that the propellers are applying, and if I give you some initial conditions, so if I tell you where the drone starts off, so what height it starts off at, and what speed, so what y dot it starts off at, you can, at least in principle, integrate this differential equation forwards in time, and that will tell you exactly what height the robot will be at any given time. All right, any questions on this so far? Okay, good. So yeah, this was kind of a warm-up, so just a 1 degree of freedom system. So now let's look at this planar quadrotor system. So again, we're going to draw some axes. So this is going to be an inertial reference frame, so reference frame attached to the ground or the room that the drone is operating in. And this is going to be my cartoon for the planar quadrotor. So often the first question we're going to ask when we encounter any new robotic system is how many degrees of freedom does the system have? So how many independent ways can the system move in? Another way to think about it is how many numbers, so how many scalars do I need to prescribe in order to completely define the configuration of the system. So I guess, yeah, does anyone want to say how many degrees of freedom this has and maybe give a justification? Go ahead. Okay. I might have maybe not been totally clear on something, but I saw a couple of other hands go up at the back there. Okay.
Y, X, and
Okay, good. Yeah. So I should have clarified this. So yeah, the system that we're going to consider has 3 degrees of freedom, and as you said, we can think of the center of mass location as corresponding to 2 degrees of freedom. So that's 2 independent ways this thing can move. So it can move horizontally, it can move vertically. There's also the orientation, and that's something we're going to consider. Maybe, I guess I didn't clarify that the drone can now change its orientation. So this orientation angle, the angle that the drone is in, we can call that theta, and that provides another degree of freedom. And these are all independent, right? So I can move purely in x, keep y and theta fixed. I can move purely in y, keep x and theta fixed. I can move in theta, so just the angle, while keeping x and y fixed. So 3 independent ways of moving, 3 degrees of freedom. Okay, so the next step, again, we'll kind of mimic this process and get equations of motion for this planar quadrotor. Again, we can apply Newton's second law. So I'm just going to write down the equations, what they look like. I'll give you a brief justification, but we won't go into the details really of the derivation. So these are the equations. So x double dot, x again is the location, xy is gives you the location of the center of mass of the drone. So x double dot is minus u1 over m sine theta. U1 has the same meaning as what we defined over there. So U1 is the total thrust. So F1, F2. As far as the board goes, yeah, U1 is just defined as the summation of those 2 thrust forces. Y double dot is going to be U1 over m cosine theta minus g, and then finally the equation of motion for the orientation. So theta double dot equals F2 minus F1 divided by I multiplied by L. So I and L are quantities that I haven't defined yet, so let me do that. I'm going to move the xy here. L is going to be, or rather 2L is going to be the length of the drone. So from the center of mass to the axis at which the propeller thrust force acts, I'm going to call that L, and then the same thing over here. And I is another physical quantity. So this is the moment of inertia of the drone, which has to do with the geometry and mass distribution of the drone. So how the mass is spread out. Question is?
The way that data is
yeah, so let's double check. So let's say theta is positive. So the way I've drawn it, this is theta positive. So in this case, the thrust forces are kind of acting in this direction. So if we look at the x component, we see that we have a force in the negative x direction.
in like the cosine.
So okay, yeah, we can check that as well. So let's say theta is 0. So in that case, the drone is completely horizontal. In that case, the thrust force is completely vertical. And so there's no x component, right? So sine of 0 would be 0, and so that checks out. And if theta is slightly positive, then the thrust force in the x direction is slightly higher, but in the negative direction. So I think this checks out, and the same in the y direction. Good. Other questions on this? Go ahead. Yes, exactly, yeah. So with the positive theta, the thrust force in the x direction is in the minus direction, in the left direction here. Good. Okay. So yeah, this moment of inertia, I guess maybe you've seen this in a physics class. Just think of it as some physical parameter. If you have a CAD model for your drone, the CAD model actually is going to tell you, well, if you have an accurate CAD model for the drone, that will tell you what the moment of inertia is. There are also experiments that one can do, like physical kind of experiments one can do with your drone to figure out what the moment of inertia for the drone is. Okay, I'm going to just define one more quantity here. Just to make the equations a bit more compact again, and again because we're going to use this notation later on. So I'm going to define U2. So I already defined U1 up there. I'm going to define U2 as F2 minus F1 multiplied by L. So this is the net moment or torque from the propellers. So from our two thrust forces. All right, so with this new notation, I can rewrite these equations. So x double dot equals minus u1 over m sine theta. Y double dot equals u1 over m cosine theta minus g. And finally, theta double dot is just u2 divided by I. And I'll call these equations 2a, 2b, and 2c. All right, so I won't in general expect you to derive these kinds of equations of motion. So if you're an MAE student, then you've again taken dynamics, you've actually seen the derivation of these equations of motion for a planar quad rotor. But yeah, I'm not going to ask you in homeworks or exams to use Newton's second law and derive equations of motion. So we're going to assume that someone, maybe your MAE friends, have told you exactly how to go through this process. What I do want you to understand, though, is like the meaning of these differential equations. So at a high level, these differential equations are telling us how the system moves, how it behaves. At a slightly more concrete level, we're saying that if I tell you what thrust forces are being applied, so that fixes U1 and U2, and I give you some initial conditions. So I give you some initial x, some initial y, some initial theta, and also some initial speeds, some initial x dot, y dot, theta dot. You can integrate these equations of motion forward, maybe using some computer software like Python, and that will tell you exactly where the drone is, what its orientation is going to be at any point in time. Right, so I guess that's the main thing. I hope from your differential equation course is something that that you are familiar with. All right, any questions on that? Okay, sounds good. Squeaky sound when I do this. I haven't taught in this classroom before. It's going to take some adjusting. I think maybe I'll come up with some like WD-40 spray it. Okay. All right. So we have these differential equations. I guess one kind of property of these differential equations is that they're second-order differential equations. So second order just means that they involve second derivatives, right? So double derivatives in time on the left-hand side. One thing we can always do is go from a system of second-order differential equations to a system of first-order differential equations. And in particular, you're going to double the number of differential equations you end up with when you go from second order to first order. So this is something in principle you've seen in your kind of ordinary differential equations course. I found that people maybe don't always remember exactly how that process works. Again, if you're in MAE, then you've seen this in dynamics. You should be familiar with it. But if not, I'm just going to walk through that process just so everyone is familiar with that process. And that's something we're going to use quite a bit in this course. So I think it's good to just go over it once in this lecture. So yeah, the goal will be to go from second order ODEs, so ordinary differential equations, to first order. And the way we do this is by introducing some auxiliary variables, so some new variables. So I'm going to define three new variables. So the first one we're going to call Vx. And again, I'll put a little triangle on the equal to denote that I'm making a definition here. So Vx is just going to be x dot. So that's the time derivative of x, the x position of the drone. Vy is going to be defined as y dot. Sorry, this is just on the board. I can't actually erase this. And omega is theta dot. It's going to be defined as theta dot. So that's the time derivative of the orientation. So with this definition, we can rewrite these three differential equations in first order form. So we're going to end up with 6 first order differential equations, so 3 times 2. So the first 3 equations, so x dot, just by definition is Vx, so we're just kind of flipping these. Y dot is Vy, theta dot, by definition again, is just omega. The more interesting ones are when we look at the time derivatives of these new variables that we introduced. So Vx dot, by definition, is x double dot, right? So Vx is x dot, Vx dot is x double dot. So we can look at this differential equation. So x double dot is minus u1 over m sine theta. So we can just write that minus u1 over m sine theta. Vy dot is u1 over m cosine theta minus g. And then finally omega dot, which again by definition is theta double dot. We can look at this last equation. So it's just u2 divided by I. Okay, so yeah, we went from 3 second order differential equations to 6 first order differential equations. First order just because all of these equations only involve one time derivative, so one dot. Basically what this allows us to do is write equations of motion in a really standard form that we're going to use throughout the course. So it's purely for convenience. There's nothing particularly deep, I guess, about going from second order to first order. We're just always going to write equations of motion in first order form, and that's just going to make things kind of notationally convenient. So let me give you the general form. Just leave the picture in place. So we're going to define the state of this system. So this is some terminology that we're going to use really throughout the course. So we're going to define this quantity x bar. So bars are going to denote vectors. So I'll try to be pretty consistent with this throughout the course. Any variable that has a bar, that's going to correspond to a vector quantity. So I'm going to define x bar, which we're going to call the state, to be x, y, theta, and then vx, vy, and omega. these three, the first three variables, x, y, theta, we're going to call these configuration variables. Configuration variables because if I specify what these numbers are, that specifies the configuration of the system. And in general, the number of configuration variables we have is going to correspond to the number of degrees of freedom, right? So each of these configuration variables gives us one independent way that the system can move. And these quantities, Vx, Vy, v omega, in this case just happen to be the time derivatives. But they're basically everything that appears kind of without the dot on the left-hand side. So what we can then do is just rewrite these equations in a kind of standard form that we use, like I said, throughout the course. And actually, sorry, just one more piece of terminology here. U1 and U2. I'll define another vector which just concatenates these. And we're going to call this the control input. So these are things that we or the robot can directly control, right? So the robot can directly control the propeller forces, which directly controls U1 and U2. So U1 again was the total thrust, the total force. U2 is the net moment applied by the propellers. Okay, so with this introduction of this quantity, which is the state and the control input, we can rewrite these first order differential equations. Let me just do that in the following form. So x dot, so the time derivative of the state, which is by definition d over dt of x, which I defined over here, y theta, vx, vy, omega. The time derivative of the state is the right-hand side of these equations. And just copy that over. Vx, Vy, omega, and minus U1 over m sine theta, U1 over m cosine theta minus g, and then U2 over I. Okay, so if we look at this system of first order equations, what we see is that it has the following form. So x dot is some function, which we can call f, of x and u. And yeah, this is going to be the general form of equations that describe the dynamics of our robotic systems. So maybe just convince yourself of this. So x dot, that matches well. Basically what I'm saying is everything that appears on the right-hand side over here is purely a function of x and u. Right? So every variable that appears here is some component either of the state or the control input vector that we've defined. All right. Again, we haven't done anything particularly kind of mathematically profound. We just went from second order differential equations that came from f equals ma to some system of first order equations. This is purely for convenience. In the future, for instance, if we encounter some new robotic system, we'll just say let the equations of motion for that system be described by x dot equals f of x u. And any like techniques that we then introduce for doing feedback control and so on, we'll just take this general form as a starting point. All right, so let me just pause for a minute and see if there are questions. I'm definitely happy to answer anything to do with the process of going from second order to first order, or just the motivation for this or the general form. Any questions on any of this?
Could you go through the motivation again?
Yeah.
Is it more than just
yes.
the standard form?
Yeah, nothing more than that. So this is convenient. It's the standard form, and maybe I'll just add one more also convenience kind of argument. Many software like toolboxes assume that things are specified in first order form. So if you use MATLAB, for instance, it has a nice function called ODE45, which allows you to integrate equations of motion, and the standard like format that you describe equations of motion there is in first order form. Similar functions exist for Python, which are things that we'll use to some degree in this course as well. Yeah, so it's purely for convenience. There's nothing much beyond that. Go ahead.
Questions?
Yeah. Okay, all right. So with functions, maybe I'll be slightly more sloppy, so you're correct. Maybe I should put a bar here as well. But I won't do that. That'll kind of be implicit. So the left-hand side here is a vector, and so we can kind of, just implicitly say that the function is like mapping to a vector quantity. You're correct. I'm being slightly sloppy, but just to reduce the number of like bars and so on, I won't put bars on functions. Good. Other questions? Okay. So the next thing I want to talk about, actually let me do that here, since we have the picture up. So far we've been assuming that these thrust forces F1 and F2 are things that we can directly specify, right? So I can just tell my drone, produce some thrust F1 in this propeller, produce some thrust F2 in the other propeller. That's not quite how motors work, right? So you don't directly get to specify a thrust. So there's some mapping from what we actually control to the thrust that gets produced by the motor. And that has something to do with the aerodynamics, right? So the propeller shape affects the thrust that you produce if you spin the propeller at a certain rate. So I just want to kind of briefly talk about that mapping. So we're going to call this the motor model. So yeah, it turns out that the thing that we directly control, actually even this is some kind of approximation, but to a very good degree of approximation. The thing that we directly control is the propeller speed. And by the speed, I mean the rotational speed. How quickly the propeller is rotating. Yeah, so really what's going on is we're applying some current, and the motor spins at a certain rate that's proportional to that direct control input of the current. We're going to ignore that part of it. We're just going to say that we directly get to control the speed of the propeller. And it turns out that there's a kind of nice relationship between the speed, the rotational speed of the propeller, and the thrust, the force that gets produced by the propeller. So this comes from some kind of aerodynamic analysis. What's really happening, one way to think about it is that this is an application of Newton's third law. So the propellers are applying a force on the air is applying an equal and opposite force on the propeller, and that's where the thrust force is coming from. And so that force kind of relationship like has to do with the geometry of the propeller, so exactly how the propellers are shaped. But yeah, it turns out that you can abstract away some of that aerodynamics, and you can end up with this really nice relationship which comes from the aerodynamics, but you can also kind of test this empirically. So the thrust force F equals some constant. So I'm going to call that constant Kf. We're going to call this the thrust coefficient. Yeah, so it's the thrust force is this constant multiplied by the control input, which is the rotational speed. Of the propeller. I'll just abbreviate that to prop squared. So the thrust force is proportional to the rotation speed of the propeller squared, and the proportionality constant, we're just calling that Kf. And we're going to give that a name, the thrust coefficient. So the particular value of this coefficient, the thrust coefficient, this constant, depends on the geometry of the propeller. So if you change the propeller, if you change the size, for instance, if you make it bigger, for instance, you might intuitively think that Kf increases. But yeah, the specific proportionality constant depends on exactly the geometry of the propeller. So, all right, let's think about a question here, which is, how can we measure what this thrust coefficient is? And that's something that's important, right? So like I said, what we're really controlling is not directly the thrust force. You get to control the rotational speed of the propeller. But our equations of motion, the dynamics, involved F1 and F2 through U1 and U2 over here, right? So we need to somehow figure out, so if we actually care about predicting the motion of the drone or controlling the drone, we need to know what the thrust coefficient is, what this constant is, this Kf is, for our particular propeller, for our particular drone. So yeah, I guess does someone have ideas for how one might go about measuring this empirically? Go ahead at the back here. Yeah? Yeah? Yeah, the speed squared, but yeah, exactly right. Yeah. So let me just draw the picture. Yeah, you described it beautifully. So you could somehow basically place the drone on a scale and turn on the propeller to different speeds and measure what the scale is measuring. You have to be slightly careful about the orientations of the scale. So if I do it the way I described it, so just keep the drone on a scale, turn on the propellers, it's just going to fly, right? So maybe you can invert it, make it go down. That's one way to do it. Or you just don't turn on the propellers high enough such that it exceeds the mass times gravity of the drone. So there's a couple of ways of doing it. But this is the basic idea, which is to collect a bunch of data where you set different propeller speeds. So I'll just call the rotor, propeller prop speed squared on the x-axis, and then the measured thrust on the y-axis, this is f, let's say. And yeah, we have a bunch of points. You might have some error in your measurement. Maybe the scale is not perfect. Maybe the thing that you're commanding is not exactly mapping to the propeller speed, or maybe you have some measurement error in the propeller speed itself. Actually, I guess this should pass through 0 if you apply no propeller speed. And that should correspond to the no force. And you can fit a line, right? So the best fit line that you get from this data. And the slope of that line exactly corresponds to Kf, the thrust coefficient for your particular propellers. So this is something that you'll get to do in the first assignment that goes out next Wednesday, so it's like 6 days from now. You won't do this experiment physically. We've done it for you. I guess the AIs, or past AIs really have done this experiment where they place our crazy fly drones on a weighing scale which has sufficient sensitivity, collected this data. So we'll give you this data and you can kind of see that this relationship holds empirically, and you can calculate the thrust coefficient for our particular drones, which are these crazy fly drones. All right. Any questions on this? Okay, so for the model that I've described, the planar quad rotor model, we actually have 3 physical parameters that we need to know in order to fully specify the dynamics for our particular drone. So the first one is the mass of the drone. So that's easy to measure. You just put it on a weight scale. The second one is the moment of inertia. That one is slightly more tricky to measure. Like I said, if you have a good CAD model, your CAD software is going to tell you what the moment of inertia is. There are also physical experiments that you can do. I can describe that maybe later if you're interested. And that's actually what we did for the crazy flies to get its like moment of inertia, and then the thrust coefficient kf. Right. So if I give you these 3 physical parameters, that completely specifies the dynamics, at least for the planar quad rotor model. Okay. So let's make it slightly more interesting now. So we pretty much understand the full. Make it stop by just pressing on it. There we go. Okay. Yeah, we pretty much fully understand the dynamics of the planar quad rotor. Again, these equations of motion allow you to predict exactly how the drone's motion will be, depending on what the initial conditions are. So what the initial x, y, theta are, and the x dot, y dot, theta dot are as well. So vx, vy, omega. If I give you those initial conditions, if I give you the physical parameters, you can, in principle, integrate the equations of motion forward to predict the drone's motion. What we're going to do next is start thinking about the dynamics for the 3D quad rotor. So that, of course, is what we really care about. We ultimately care about controlling the crazy fly drones in our first lab. Let's again think about how many degrees of freedom this system has. So the 3D quad rotor has. Degrees of freedom, again, just the number of independent ways a system can move, or equivalently, the number of numbers, the number of scalars I need to give you in order to fully specify the configuration of the drone in space. So yeah, I guess I want to take a crack at this. How many degrees of freedom? Go ahead. 6, good. And why? Okay, perfect, yeah. So we have 6 degrees of freedom. So the position of the drone, I can specify with 3 numbers, so x, y, z. These 3 numbers could specify the center of mass location of the drone. I still have to resolve the orientation, and I can do that with 3 numbers. So hopefully the position part is clear to everyone. The orientation part is a bit more tricky. So I'm going to describe how, like, exactly what these 3 numbers are, what the options for the 3 numbers are, and the specific, I guess, concept we're going to use to describe orientation. This is Euler Angles. And yeah, Euler Angles are really common for describing orientations for drones. There are some other possibilities as well, so quaternions, axis angle conventions, and so on. In this course, we're just going to stick with Euler Angles, and I'm just going to give you a brief kind of crash course on Euler Angles. Maybe just a quick show of hands. How many of you have seen Euler Angles before? Okay, not everyone, maybe 60% or so. Okay, good. All right, so I won't be wasting everyone's time with this discussion. Maybe you have seen it, maybe it's a good refresher, because it does cause a fair bit of confusion sometimes. Okay, yeah, like I said, these are this is one way to specify orientation of some 3D object. And the way this is going to work is we're going to first define some reference frame. So these are three directions, EX, EY, and EZ, that form a right-handed frame. So you can see that EX cross EY is EZ. I'm going to label this frame as I. So I is our inertial reference frame, so some reference frame that's just attached to the ground, attached to the room that the drone is going to be flying in. The more maybe interesting reference frame is the one that's going to be attached to the drone. So just imagine like a plane that corresponds to this plane that the four rotors are in. I'm going to define three directions: BX, BY, and BZ. And X is going to be forward, so maybe let me just write it here. So B just stands for body. These are three axes, three directions that are attached to the body of the frame. So BX is in the forward direction. The drone is facing that way. BY is to the left. And BZ is just straight up from the perspective of the drone. And this actually is the convention we're going to use. So yeah, just imagine that forward is here. The drone actually has a little indicator that tells you which way is forward. So there's a little kind of piece of the PCB that's sticking out. You'll read about that in the instructions when we actually start working with the hardware. But just imagine this is forward. So BX is some direction, some axis that's attached to the drone and points in its forward direction. BY is to the left, and BZ is up. So again, this forms a right-handed frame, right? So BX cross BY, you can maybe just double check using the right-hand rule, is BZ. And this is attached to the drone. So as the drone moves, these directions move with the drone. And the origin, let's say, is just at the center of mass of the drone. All right. So with this, with these conventions, we can introduce Euler angles, which then allow us to describe the orientation of the drone. So here's one way to specify the orientation of the drone in 3 dimensions. So we're going to follow a process that's going to allow us to describe or specify the orientation, let's say, of B. So this frame of reference, the body frame, we're going to call that frame B, relative to frame I. So relative to the inertial reference frame, so relative to the room, again, if you like to think about it that way. And we're going to describe this process where we first start off, maybe step 0 is start off by aligning B with I. So the 3 body directions, BX, BY, BZ. Just imagine that you start off by placing the drone such that the BX direction is aligned with EX, BY is aligned with EY, and BZ is aligned with EZ. The next step, the first step, is then going to be to rotate the B frame about the direction EX, so about the inertial x direction by some angle, which I'm going to call phi. And we're just going to call this angle phi, we're going to call that rho. So physically, what this means is you start off with the drone in this configuration. Again, imagine that EX is this way, EY is this way, EZ is up, BX is aligned with those axes. So you just rotate the drone about the inertial x-axis by using the right-hand rule by some angle phi. Right? So you align your thumb with the EX direction, and you rotate. The drone is going to be then kind of rolled like this. So does that first step make sense? I guess any questions on that? Okay. So let me describe the second and third steps. So the second step is going to be to rotate B about the EY direction by another angle, which we're going to call theta. And I'll just give this a name as well. We're going to call this the pitch angle. And finally, the third step is to rotate B about the EZ direction by another angle, which we're going to call psi. We call this the yaw angle. All right, so let me just illustrate it once maybe with the physical drone. I also have these Wolfram Alpha demonstrations, which I think should be pretty useful if you haven't seen this before. So again, you start off here, rotate about the inertial x-axis. So that's the roll angle. You then rotate about the EY direction. So EY, remember, was to the left. So I line my thumb along the EY direction, and I apply the right-hand rule. So that goes this way. And then EZ again goes up. I align my thumb with the EZ direction, apply the right-hand rule, so that goes like this. So I guess any kind of high-level questions on that, I'll walk through that process again with Wolfram Alpha, and that might make it more clear. Yeah, let me actually just do that. Maybe while I'm pulling that up, I can see if there are any questions. So these angles, maybe just while this is coming up, these three angles, phi, theta, and psi, are known as Euler angles. So let me just go through the process. So just a caveat, this specific convention that I'm going to illustrate here doesn't quite match exactly this convention. So I'll say a bit more about the different conventions in a bit. This illustration is just to give you a picture of what this kind of general process looks like. So we have two frames. So right now they're both aligned, so you, I guess, cannot tell the difference. One of the frames, the inertial one, is the one that's going to be labeled with the little arrows as the pointers. The body frame, the one that's attached to the body of the drone, that has little spheres at the end. And the X, Y, and Z directions, those are just labeled with the different colors. Right, so we just start off with the two frames aligned, and then we rotate about one of the axes, one of the inertial axes. In this case, we're rotating about the vertical axis. You can think about that as a Z, for instance. All right, so I do this one rotation. So let's say I go all the way up to here. I then rotate about the inertial green axis. Right, so that's what this is. And then finally, I rotate about, I guess, which one is this? Can someone tell? This is the inertial z-axis again, right? So I did three different rotations. The first one was about the inertial z-axis, then the inertial green axis. Which one is that? That's, you can think of that as y. Maybe x is red, green is y, z is blue. And then the inertial z-axis again. So let me just go through that process one more time. All right, so inertial blue, the inertial z-axis, that's this rotation. Inertial green, that's inertial y, that's this. And then inertial z again. So that's one particular Euler angle configuration. So the claim I'm going to make is that no matter what orientation the drone is in, so however it's configured in orientation, I can describe that orientation by giving you three numbers, which are these Euler angles. So I guess, does that claim make sense? And maybe any questions again on this process of rotations? Okay, yes, go ahead. Yes, good. Okay, so that was going to be the next thing I emphasize. So the fact that there are multiple conventions, so I actually illustrated two different conventions here. So the first one, we were doing these rotations in a specific order. So first about EX, then about EY, then about EZ. So that has a name. Let me just turn on the lights again. So what I described on the board over here, so this is called the space 1, 2, 3 convention, Euler angle convention. So the reasoning for where this name comes from, space is because we're doing the rotations about the inertial axes, so the axes that are just fixed in space, so not fixed to the body. And 1, 2, 3 has to do with the order, right? So we're first doing the rotation about the EX direction, so that's the first direction, then the EY direction, that's the second, EZ is the third. So maybe just as a check for whether we understand the terminology or not, what was the convention, or what name would you give to this convention that I illustrated here? I guess right at the back, maybe? Yeah. 3, 2, 3. Okay, good. So space 3, 2, 3. Space again because we're doing the rotations about the spatial axes, the inertial axes. 3, 2, 3 because we did Z, Y, Z. Right? So that's 3, 2, 3. That's where the naming convention comes from. So if you count up the number of these different conventions, that's 12 different space conventions. To make things even more interesting or confusing, depending on your point of view, there's another way to do these rotations, which is to not rotate about the spatial directions, so not do the rotations about the inertial directions, but to do the rotations about the body directions. Let me see if I can just illustrate that over here. So here we're rotating. You can think of this as doing the rotation about the body Z direction. We then rotate about this. So you can see that this rotation is happening about the body green direction, right? And then finally this one is again happening about the body blue direction. Let me just maybe go through that again. First one, body Z, so the Z direction attached to the body. The body again is labeled with the little spheres at the end. Body Y, that's this one. And then body Z again. So this convention that sorry, yes, go ahead. So with this one, we didn't actually. So this was just blue, green, blue. There is a way to do it about the red one as well. So that would be yet another convention. I don't think this Wolfram alpha demonstration quite does that. This just illustrates a couple of different conventions. Again, maybe just as a check, what would you call this convention that I just described, or that I just illustrated? So it's still 3, 2, 3, but it's not space but body, right? So what I just illustrated, you would call that the body 3, 2, 3 convention. So there's 12 more of these conventions where you do the rotations about the body axes. And one of the conventions you would do one of the rotations about the red one as well. Okay. All right. Let me, I guess, just maybe synthesize. I'm going to switch back again to the question. Yes. Sorry, the projector is actually making a little bit of sound. Yes. Yes. Yes, exactly right. Yeah. Maybe I'll just repeat that. So with the space ones, you're doing the rotations about these fixed axes, like the fixed inertial axes. With the body ones, you're doing them about axes that are kind of changing, right? So the intermediate axes. So once you do the first rotation, that changes where bx, by, v, z are. So you do the next rotation about that new direction, and then the third one about the newest direction. So I guess I'll just make a couple of high-level comments here. The first one is we're not, in this course, going to be worried about the multiple different conventions. The space 1, 2, 3, in some sense, that's the cleanest one, right? Everything is happening, all the rotations are happening about the spatial axes. The order is clear, just 1, 2, 3, x, y, z. This is the one we will use for this course. Another comment is that in practice, so I guess beyond this course, you might encounter these different conventions. And in practice, this causes a massive amount of confusion and errors. So just as a kind of quick anecdote, so I've spent, or I wasted, I should say, something like 3 months as a PhD student because I wasn't completely sure what convention I should be using. So I was working with a fixed-wing aircraft, a small drone, trying to make it avoid the obstacles. I had a motion capture system, so Vicon motion capture system, if you've seen those. That's supposed to track the position and orientation of the drone in real time, so at 120 hertz. That gives you the orientation in some Euler angle convention. And my dynamics model I had written down for the drone was in a certain Euler angle convention. I thought I had like double checked that those two conventions were identical. It turns out I should have triple checked it because they weren't identical. And yeah, it led me to wasting like about 3 months because I wasn't like fully careful. So if you're working with a team like beyond this course, not for this course, we're just going to use this one. But if you're working with some team, or if you're working with another like piece of equipment like a motion capture system, really like double check, triple check that you know exactly which Euler angle convention is being used by what or by whom, because it causes a really like massive amount of confusion and errors in practice. All right, questions on this? Okay, so yeah, I guess we have maybe 10 more minutes. So what I'm going to do, I guess, in the last 10 minutes is just describe or just set up some of the terminology we'll use for describing the 3D dynamics of the drone, or the drone, like dynamics for the 3D drone. So we'll just say what the states are and what the control inputs are. I won't write down the equations of motion yet. We'll do that kind of briefly in the next lecture. And maybe just before I do that, I'll just re-emphasize the point that we will be able to write down the dynamics in a kind of general form. Which is x dot equals f of x and u. X is, again, the state. U is the control input. So the last 10 minutes or so, I just want to say for the 3D quad rotor, what are the states, what are the control inputs? And then in the next lecture, I'll kind of briefly go over what the equations of motion look like for the 3D drone, which will then allow us to use feedback control techniques, which we'll talk about to make the drone hover. So the states the 3D quad rotor, the state vector x. Actually, I guess if someone maybe want to guess how many dimensions, like what's going to be the dimensionality of the state vector. So with the planar quad rotor, it was 3 degrees of freedom. We ended up with 3 second-order differential equations, which we then converted to 6 first-order differential equations. Here we said this was a 6 degree of freedom system. I guess if someone want to maybe just guess how many states, like what's the dimensionality of this state vector going to look like? Go ahead. Say it again.
6.
6. Okay. Why would you say that? Or what? Okay. So I guess it didn't quite with the planar quad rotor, right? So with the planar quad rotor, we said that there were 3 degrees of freedom, and the state vector was 6-dimensional. So here it's going to be the same kind of relationship. We're going to end up with a 12-dimensional vector that describes the state. And roughly what that corresponds to, the first 6 dimensions of the state vector are going to be the configuration variables. These are the variables that kind of correspond directly to the degrees of freedom. The other ones, the remaining 6, are going to have to do with the rates, the time derivatives of the configuration variables. So let me just say what the states will be. We'll again go through this, go through these dynamics in this form more carefully in the next lecture, but just to set things up. So x, y, z. This is the center of mass, COM position. So these are the variables that correspond to the translational degrees of freedom. Phi, theta, phi. These are the Euler angles. Again, using the space 1, 2, 3 convention. So these are the first 6. And then we're going to have x dot, y dot, z dot. Those are the time derivatives of the positions. And then finally, there's a kind of choice here. So we could go with phi dot, theta dot, psi dot, the time derivatives of the Euler angles. It turns out it's slightly more convenient to use some other variables, p, q, r, which are going to be the angular velocity vector. So if you haven't seen angular velocity before, I guess don't worry too much about it. Just think of them as something that's related to to phi, theta, and psi dot. So it tells you the angular velocity, the angular rotation of the drone, so how quickly the orientation of the drone is changing in different directions. Yeah, I'll say maybe a bit more about that in the next lecture. But this is what we'll use as our state vector. And then the control input vector. So we could use the 4 propeller thrusts, so F1, F2, F3, F4, and that's like a perfectly kind of reasonable choice. It turns out that it's slightly more convenient, and by convenient I just mean the equations you end up with just look more compact when you work with a slightly different control input vector. So it's still going to be 4 numbers, but they just have a slightly different meaning. So the first component of the control input vector, I'm going to call it FTOT, F total. This is the total thrust. So just the magnitude of the total thrust produced by the 4 propellers. And the other three components, I'm going to call them M1, M2, M3. So this is going to be the moment, the torque produced by the four propellers about the body X axis, Bx. This will be the moment about By, and the moment about Bz. So this is kind of similar to what we did with the planar quadrotor, right? So if you think about, I guess I raised the equations now, but if you look back at the equations of motion we wrote down for the planar quadrotor, we wrote them down in terms of two control inputs, U1 and U2. U1 we defined to be the total thrust, U2 we defined to be the total moment. So this is analogous. So U1, the first component, F total of the control input vector, is going to be the total thrust produced by the four propellers. Now, because we're working in 3D, the net moment, the net torque, is not just about one axis, but is about three different axes, Bx, By, Bz. So the control inputs, M1, M2, M3, are going to correspond to the net moments, the net torques produced by the propellers about these three axes. I'll go into more detail about this in the next lecture. But just as kind of a quick point, it turns out you can go back and forth between these two representations. So if I give you F1, F2, F3, F4, you can calculate what these are, what the net thrust is, what the net moments are. And if I give you these four numbers, it turns out you can invert that relationship and get these. So in some sense, they're equivalent. But like I said, it's just slightly more convenient. The equations look a bit more compact if we go with this representation. All right, so yeah, in the next lecture, we'll use this state and control input and write down the equation of motion for the 3D drone. I'll see you next week.